In this video, I'll be addressing the force diagram for Gabe's solution to pushing the boxes across the ice in the hockey problem, where he stacks the two boxes on top of each other. So in this case, we'll only be addressing the force diagram because parts B through D will be essentially the same to Andrew's idea because we have made the assumption there that we'll be taking this as a single crate with double the mass. And so the idea will be very similar. We'll just have to adjust for the mass, and that would change the values a little bit, but everything else will stay exactly the same. The force diagram will be a little bit different, though, because we're still treating the two crates as separate. So let's see what we can do with that. When it comes to crate A, we can see that we've got Gabe pushing on the bottom crate there. And so our push is still going to be only on crate A, and so we'll draw on that push force there. And we can see that A is going to have some friction across the ground. It's going to be moving to the right. And so we should have a friction force acting on it in the reverse direction. So friction force will go to the left there. The tricky thing is figuring out now what happened with crate B and anything else that should still be there on crate A, in addition to what we've shown so far. The tricky part about this is that the two crates will exert some friction force on each other. And so in this case, because crate B is stacked on top of crate A, we can think of it having a wood on wood, if these crates are made out of wood, friction force, which will be a little bit different from the friction force that we would see with the ice. We don't necessarily have to quantify this because, again, that's going to get stuff that's more complicated than what we're expected to deal with in this class. But we are going to have to show what direction it goes. This can be a little bit tricky to think about because we know that the crate B needs to be moving in the forward direction by the end. Logically, we know that's going to be the case, but we might expect the friction force to be in the reverse direction here. So let's think about why we're actually going to have some kind of friction force between the two crates going in the forward direction here on crate B. The reason for this is that if we think about what happens here, if there was nothing connecting the two crates together, and so no friction force, if we were to have Gabe push on crate A, that would actually push crate A out from underneath crate B. And so later we'd see something like this, where we've got crate A moved a bit ahead, and crate A, or crate B, would still be back where it was originally. And that's going to create a pretty dangerous situation for Gabe, so he should be pretty thankful that there is going to be that friction force between them. So relative to crate A, this kind of comes back to some of our motion stuff where we have to think about our frame of reference. Relative to that, crate B would have been moving backwards. It would have been moving in the left direction. Because this relative motion should be opposed by the friction force, that's why we have a friction force going forward here. And so the friction from crate A acting on crate B is going to end up pushing it in the forward direction in this case. What this means is that B should be exerting an equal but opposite force on crate A. And if we draw that in, we should have something like this. So it should be going to the left there. We can call this friction from B acting on A. And so we've got another force going in the backward direction there. What we see here is that this ends up being somewhat similar to what we saw in Daniel's situation. The only thing missing is that we don't have any friction force from the ice acting on B because it's not in contact with the ice. Frankly, the only thing that B is in contact with is crate A, and so that's the only thing that's able to exert a horizontal force on it. So once we've got all these forces in, this is going to complete our force diagram for the two crates here. Again, this is probably beyond what you would need to know for anything in a testing situation, which is why for the following questions, you're allowed to make that simplifying assumption that these two are essentially a single large crate. But I want you to get a chance to see if you could play around with this and come up with some idea for what's going on here to explain the motion of the two crates. So this will complete the treatment for question 3, Gabe's situation. Again, if you want to look into the calculations, go back and take another look at the videos from problem 1, because the situation will be essentially the same, with the only difference being that the mass will change, because we're accounting for this as 2 crates mass, which would be 110 kilograms as opposed to the 55 kilogram mass per crate.